Hello everyone. In this video, we are going to talk about the various modes of operation of shift registers. So in the previous video, we mentioned these four kinds of operations of shift registers: SISO, SIPO, PISO, and PIPO. Now we will talk about each of these in detail. Alright, let's first begin with SISO, serial input, serial output shift registers, right? These registers, they accept data serially, one bit at a time, on a single line. That is, we have one single input line, the data comes in serially, one bit at a time. And the stored information is produced on the output in a serial form as well. So, very basically, this is what the entire process of SISO shift registers look like. This is a register, a very basic description. These are the four flip-flops we're talking about. For illustration purposes, we have used a 4-bit register, right? So we have four flip-flops. The data goes in from one end, it comes out from the other end. The same thing is happening here, except the direction of the flow is different. That is the only difference between these two, right? Data moves in from left to right. That is, the shifting is performed. The shift operation is shift right. Right? Data is shifted. This flip-flop, this first flip-flop, takes this data, gives it to the next flip-flop. The second flip-flop then takes input from the previous flip-flop, gives it to the next one. The third one does the same. The fourth one finally takes the input from the third flip-flop and gives it out. And that is the entire operation. In this case, the shifting is left. We have left shift, right? So each of these flip-flops is shifting the data to the left. This is what essentially SISO registers do. Data comes in serially, one bit at a time. This bit is shifted from one flip-flop to the next, and then finally the data comes out from the other end, also in a serial format. Let's take a look at the design of a SISO register in a bit more detail. So we have four D flip-flops arranged in a cascade. The output of the first flip-flop is the input to the next one, and then the output of this flip-flop is the input to the next one, and so on up to the end. We have the data goes in from this line, serial input, data comes out of this line, this is serial output. This is the complement of the output, which you'll understand if you just recall the operation of a D flip-flop, right? So serial output complement, and then the clock, very essential component. A common clock pulse that controls the flow of the data, that is the shifting of the data from the first flip-flop to the next, and from the next to the next, and so on through the entirety of the register. So a common clock pulse that goes to all the flip-flops simultaneously. Try to understand the operation of a serial input serial output shift register by taking a look at an example, right? So say we have 4 bits 1010, and say we want to enter this data into a shift register. A register is a temporary storage unit, right? So we want to store 1010 into this data. Let's go with the previous example, this basic 4-bit register. So how do we store 1010 into a SISO register? So this is the initial setup of your register, right? All the bits are 0 for now. All right, initially the register is cleared. There is no information in the register at this moment. And then the first bit comes in. So how do we begin this? We begin it from this side. All right, so the first data bit is 0. Initially the register was in a clear state, and now the first input comes in. 0 comes in, and the first D flip-flop, the first flip-flop, it outputs 0, right? So I'm not going to be showing you the truth table of a D flip-flop. You've already seen it, you already understand it. So if you need a refresher of what D flip-flop does when it gets 0 or when it gets 1, you will have to just take a quick look back, right? So the first data bit comes in, it's 0, and the output of the first flip-flop is also 0, right? After the first clock pulse. So I said earlier, it's important to understand the register just doesn't work unless there is a clock pulse. So all of the operation, all the shifting, everything is controlled by the clock. So on the first rising edge of the clock, that is the first clock pulse, the first bit is shifted by the first flip-flop, and then the second data bit, This is this one. Okay. The second data bit comes in after the application of the second clock pulse. It goes in from one end of your register. So the output of this register, so the input is 1, the output is 1. The previous input was 0. This is what the second flip-flop gets, right? This is what the second flip-flop gets, and that is why this is what the second flip-flop generates. Okay? This is after the application of the second clock pulse. And then after the third clock pulse, the third bit is entered. Third bit is entered from the left. The first flip-flop gets the third bit. It produces the output. It's the same bit. The second flip-flop at the application of the second clock pulse had received 1. So it outputs 1, right? The third flip-flop had gotten 0 previously. So its output is 0. And you can see how the bits are shifted from left to the right. And that is why it's a shift register, and that is why it's a serial output shift register, because the data is going in serially, right? This is after the application of the clock pulse 3, and after the application of clock pulse 4, you can see what would happen. The fourth bit will go in. The fourth bit is now going in 1. So the fourth flip-flop had gotten 0, so its output is 0. The third flip-flop, last time it got bit 1, so its output is bit 1. Previously, the second flip-flop had gotten bit 0, so its output is bit 0. And after the application of the fourth clock pulse, data bit 1 came into the first flip-flop, so that's why its output is 1. Right? So after the application of the fourth clock pulse, a 4-bit number is completely stored in the register. Now, if you were to take out this information from this register, it will come out in this form only, 0, 1, 0, 1. But right now, we're not taking it out. Okay, so this far, we have only seen how the data is entered into the register and stored. So how many clock pulses did you require to store a 4-bit number in a 4-bit register? 4 clock pulses. At the first clock pulse, the first bit goes in. At the second clock pulse, the second bit goes in. At the third clock pulse, the third bit goes in. After the fourth one, the fourth bit goes in. If you had a larger register and if you had a larger number, that's how many clock pulses you would have required. All right. So now let's see how this number that we previously stored is going to be shifted out of the register. Right? So first we moved our data 1010 into a cleared register, and now we're going to be shifting it out because now we have stored it. Now we want to take it out. Again, it will come out serially. Right? So let's see how that happens. So this is the current state of your register. This is the last state we discussed here. 1 0 1 0, right? 1 0 1 and 0. So when we're going to be taking out the data, this is going to be the first bit, right? This is the bit that was inputted into the register after the application of the first clock pulse. So this is the first data bit that entered the register, and this is going to be the first data bit that will exit the register. Right? So after the 4 clock pulses, the register contained 1010. Now we'll see how to take it out of the register, how to take this data out of the register. So for clock pulse 5, right, it will continue from the previous cycle. This is entirely part of one operation, moving the data into the register and then moving it out. It's one whole operation. So now clock pulses will begin where we left off previously. Clock pulse 5. When clock pulse 5 comes, this 0 will have been taken out. This 1 will move here, and that's what's happening. This 1 moved, and so at the output end, we had the next bit. Then after clock pulse 6, the next bit, which was this one, it came out, and we took it out. And then after the clock pulse 7, the final bit, which was this one, comes out, and we get the 4th data bit. This is after clock pulse 7. And then finally, after clock pulse 8, the register is entirely clear. So we can't stop we can't stop at clock pulse 7, because even though we have gotten our last bit, we did get 1010 out of the register. See, first we got 0, then we got 1, then we got 0, and we got 1, right? But the point is, we have to return the register to the same state it was in before data moved in. So earlier, if you remember, at the very beginning of this entire process, the register was 0. All the outputs were 0. And that is what we need it to be after we've taken out the data. We need it to be 0 once again. That is why we have used a final clock pulse. That means to store a 4-bit data in a register and then take the same 4-bit data out of the register, we needed how many clock pulses? 4 plus 4, right? 4 to move it in, 4 to move it out, and return the register to its initial cleared state. So clear is nothing but all the bits should be 0. That's what clear means. So this is how serial input, serial output registers work. Data goes in serially and data goes out serially. All right. Let's talk about now the second type of shift registers, where the data goes in serially but it comes out parallelly. Right? Again, very much clear from the name itself. A SIPO shift register is loaded with serial data. The input is serial, 1 bit at a time. The outputs are disabled as long as the data is being loaded. And then once all the data enters the register serially, it is taken out in parallel form, that is simultaneously. The data goes in sequentially, 1 bit at a time. As long as it's going in, all the outputs are disabled, and when all of the flip-flops have their respective bits stored in them, then all the outputs, the outputs are enabled all together at the same time, and the data comes out simultaneously. All the bits can be outputted simultaneously, and that is the very basic and simple description of how SIPO registers work. Data goes in serially, but it comes out all at the same time. Now, this is what the design, again, we're taking a look at the internal design of a SIPO register. Again, we have designed it using D flip-flops. And again, we have common clock pulses. This is a must. This is universal. It has to be there. Data is going in serially, as you can see. The difference between this and SISO register was there were no taps in that case. In this case, we have taps and we are taking out the 4 bits of the data out. And we can take them out at the same time. This was not available in SISO registers. There was only one output line here, so that the data had to come out serially. But in this case, we have taps on all the outputs, on the 4 outputs of the 4 flip-flops. And the only reason we have these taps is so we can take out the 4 bits at the same time. Logically, if you had to design a logic symbol, it's very simple. Data input line, the clock line, and the outputs. So this is a 4-bit register. If you had an 8-bit register, you would have 8 output data lines. Right? So this is very basically the design of a SIPO register. Now let's take an example to illustrate the operation of a SIPO register. So this is a table which shows how a 4-bit binary number 1001, just an example, is shifted to the outputs of a SIPO register. So how does it work? This is the first flip-flop, the second one, the third one, and the fourth one. So this is the left end, this is the right end. Initially, your flip-flop is cleared. All the outputs are 0. And then we start to move our data 1001 into the register. Now remember, data will go in serially. Each of the bits will go in one at a time. So initially, your flip-flop is cleared. All the outputs are 0. And then the first bit goes in. This one, right? This one, it goes in. Stored in the first one. The rest of the outputs are still 0. They have nothing to output. And then next bit goes in. So what happens to the previous one? It is shifted one position to the right so that room is made for the next bit. Right? And these still stay 0 because they have no input right now. And then third bit goes in, right? So the first one moves one position to the right. This one also moves one position to the right, so that room can be made for the next bit. And finally, the last bit goes in. So the previous bit is shifted, the previous bit is shifted, the previous bit is shifted, and room is made for the new bit. So now this is the arrangement of your register. We have 1 0 0 1. This was the data. It has been stored in the register sequentially. Now all you have to do to take it out, just open all these tabs, open them all up, and you get all the 4 bits at the same time. You get 1 0 0 1 simultaneously. And that's the entire operation of a serial input, parallel output shift register. Now let's move on to the third kind of shift register, parallel input serial output, PISO. So again, from the name itself, you can see that the data must move in a parallel format, right? So simultaneously all the bits are entered into the register, but the data is read out sequentially, right? So this PISO register behaves in a way which is opposite to a SIPO. In SIPO, data moved in serially, it came out parallelly, that is simultaneously. In PISO, the data bits are entered into the register simultaneously, but they come out serially. Right? So very basically, this is how it works. Again, a very simple illustration of a shift register. We have 4 flip-flops. The inputs are simultaneously opened so that the data can enter the register at the same time, all the 4 bits at the same time. And then data is read out and shifting is involved. And you have to understand, see, when the data moves in, so suppose we have a 4-bit number 1010 that is entered into the register, but the outputting of the data has to happen sequentially, which means that when the bit stored in this location is read out, then the bit stored in this location has to move one position to the right so that that bit can then be read out. And then that bit is read out, so the data bit, the bit that was initially stored in this register has to be moved here, and then again it has to be moved here so that the next bit can be read out, and the same goes for the 4th bit. Right, so this is where shifting is involved. Alright, so this is the design of a basic 4-bit PISO shift register, again which we have constructed using DE flip-flops. Now most of it will seem familiar. We have the 4 flip-flops, we have the clock pulse, this is essential. What additional things you'll notice in this circuit as compared to what we've seen previously is these collections of gates, these additional combinational circuits. And this is what actually makes a PISO register work. Because again, remember, the thing about PSIO registers is that the data comes in parallelly, that is, the data is loaded into the register simultaneously, but it must be taken out serially. And this is how these gates are actually what makes it work, right? So this will become clearer just in just a moment. First, this is the logic symbol, which you can take a look at. See, again, we have this line. Again, the purpose of this line will become clear in just a moment, right? So we have the shift and load line, we have the clock, we need this is the data input, data, all the bits will be loaded simultaneously, and this is the output line. Again, this is for a 4-bit register. If you had 8-bit register, the number of data input lines would have increased, but the output line, because this is serial output, so we only need one output line. All right, so let's now talk about the operation of a PISO register in a bit more detail, right? And the first thing to notice about a PISO register is that it operates in 2 modes. So we have a load mode and we have a store mode. So let's first begin with the load mode. What happens in a load mode? Now, when the shift and the load bar line is low, this one, right? When this line is low, which means when this is 0, what happens is AND gates G1, G2 and G3 become active. Now, again, this has to do with the basic concepts that you read about when you learned about gates. So we're not going to be repeating that right now. You have to understand how a NOT gate works, how a AND gate works, how OR gates work, right? So you can just pause it for a minute and just go back and refresh the concepts and then come back, right? So what happens is when this line is low, when this is 0, G1, G2 and G3 become active. What that means is, what it means when we say it becomes active is that they behave like open circuits. So they let whatever input they have to become the output. So they let it pass through them, right? Like open circuits. So when G1, G2 and G3 are behaving like open circuits, they pass D1, D2 and D3. And what this is basically, this is the 4 bits of your input. D0, D1, D2, D3 are the 4 bits of your input data, right? So what they do is there's no restriction on the passage of D0, as you can see in this figure, right? So nothing is stopping D0. D1, D2, D3, however, have to pass through these combinations. So when G1, G2, G3 are active, they pass D1, D2, and D3 to the corresponding flip-flops. So D1, this is open now, so this will pass on to this. Okay, it doesn't go in at the moment, right? This is important to understand. D2, again, D2 will pass through the system and it will land here, and then D3 will also pass through the system and it is here, right? It's important to understand right now that only the bits have been passed through this circuit and they are now at the gate, at the entrance point of the flip-flops, right? And then what happens? See, let's not forget the clock, because we keep saying that the entire operation of registers is based on the clock. So far we have seen the shift and load line. So where does the clock come in, right? The clock, what happens is, now all the data is at the entrance points. So this just comes in directly, right? So all the data bits are at the point, all at the gates, at the entrance points of the flip-flops. When the clock pulse comes in now, these inputs will get loaded into the corresponding flip-flops, right? So the passage of the bits through this system is controlled by this line, but the actual loading of these bits, the bits that were waiting at the entrance point of the flip-flops, the loading of them into the actual flip-flops, they have to move into the registers, right? So that moving into the flip-flops is controlled by the clock. And this is where these works in association with the clock pulse. It's very, very important to understand, right? There's a difference between saying that bits pass to the flip-flops and saying that the bits are loaded into the flip-flops, right? So the passing of the flip-flops is controlled by this line, but the actual loading of the bits into the register, into the flip-flops, is controlled by the clock. So now loading has been completed, right? You can see D0, D1, D2, D3, the 4 bits of your data have been loaded into the flip-flop, and that loading was done parallelly, simultaneously. All of them were entered into the register, the corresponding flip-flops of the register, at the same time. And now it's time to actually perform the second part of the operation, right? For that, the PISO register has to go into the store mode. And now what happens is this line, it becomes high. So earlier it was 0 for the loading. Now it becomes 1. And now when this becomes 1, what happens is G1, G2 and G3, they become inactive now. Now they are going to behave like closed circuits. They're not going to let anything pass, right? And this is something we mentioned at the very beginning of this discussion, that once the flip-flops have been loaded, they cannot be loaded again unless the data which is already stored in them is taken out, right? It makes sense. They can only store 1 bit at a time. So these bits have been stored in the previous phase in the load mode, right? And now these gates will become inactive. They will stop accepting any input, right? So data can no longer be loaded. Data loading becomes impossible. But then when this line is high, G4, G5 and G6 become active, right? G1, G2, G3 will become inactive, but G4, G5, G6 will become active. What that means is now these gates are going to behave like open circuits. And that is when shifting will take place. Because remember, the data was loaded into the flip-flops simultaneously, and that is fine. But now it's time to take it out, and that has to be done serially, which means the bit which was here has to be taken out, and then the bit which was here has to move here so that it can be taken out, because there is only one output line, there's only one exit. Okay, so shifting has to take place. And how will that take place? Again, it's important to understand it at this point. G4, G5, and G6 are now active, which means they will let data pass through them, right? So when clock pulses, again, clock pulses are important because that is what dictates the flow of the data. So whatever data bit was in this position in this flip-flop will be taken out. One bit will be taken out after the application of the clock pulse, right? So this data has come out, that is fine. Now this data has to move here, right? And this is where the gates come in. G6 is active, which means whatever bit was in this flip-flop can simply move through this gate into this gate, into this flip-flop. And then after the application of the clock pulse, that bit can be taken out. And then whatever bit was here will move from G5, because G5 is active, it will move through this circuit into this flip-flop, and from this flip-flop into the next one, and then that can be taken out. And the same goes for this, right? It goes from this gate to this gate to this flip-flop, and from this entire operation again, and then entire operation is repeated again, and then finally that bit can be taken out. So you see how with the help of shifting, and all of that shifting is going to be controlled by the clock. So with the help of the shifting, bits are taken out of one flip-flop into the next one, into the next one, into the next one, until they can be all taken out. And that is how data went in parallelly, but it came out serially, right? Again, it's very important to understand, and it's very, very simple if you think about it. Load mode and store mode, right? Okay, let's take an example, again, for some better understanding of how this entire thing works, okay? So this is a table showing the 4-bit binary number 1001. As an example, we have taken 1001, and let's see how 1001 is shifted from the input to the output of a PISO register. So initially, again, we start from a clear state. All the outputs have to be 0. The outputs of all the flip-flops, they will be 0. And then writing. Writing is essentially loading, right? So we can say you write into a register or you load a register. It's basically the same thing. So writing is taking place. Again, writing will take place simultaneously. So D0, D1, D2, D3 will all be loaded into the register at the same time. And now it's time to take the data out. So all of these steps pertain to the taking out of the data, which will involve shifting. Okay, so now the data has been loaded. The flip-flops have information 1, 0, 0, 1. Okay, so this was at the 4th flip-flop, so this can be taken out simply, right? And then what happens? This is moved here, this is moved here, this is moved here. Okay, and then this is the output at the 4th flip-flop. So again, this can be taken out simply, and the rest of the data will then have to shift one position to the right. Okay, and then this is at the edge of the register, this is at the end of the register, it can be taken out as well. And then the remaining information has to be shifted, and then again this is at the 4th flip-flop, so it can be just taken out. Okay, and this is how a PISO register works. So the writing or the loading happens all at the same time, but the reading out of the data is done with the help of shifting. All right. So now let's, oh, before moving on. All right. So far we have seen that we have designed this PISO register using this system of gates, right? This is the combinational circuit that we used, but this is not a necessity. So you must have realized this by now, that you can design the same circuit in a variety of ways, right? So one of the ways is using a multiplexer. So you can see again, this is a 4-bit PISO register. The functioning is exactly the same. It operates in the same manner. The only difference is, instead of using that setup of these combinations of these AND and OR gates, we have used multiplexers instead, right? So there are many ways to design the same thing. A PSIO shift register can be constructed using multiplexers as well. All right. Finally, PIPO, parallel input, parallel output. So the data goes in at the same time, all the bits come out at the same time. Very simply, this is how it looks like. All the data going in at the same time, and the bits coming out at the same time. This is the design of a basic PIPO register. Again, designed using D flip-flops. We have the clock. Simultaneously, it will um, monitor the flow of the data. We have, since this is a 4-bit register, we have 4 input lines and we have 4 output lines. Again, you can see how this works, right? It's very simple. Now, just a quick recap before moving on to the next segment of this lecture. Just a quick recap to show you the various kinds of operations of shift registers, right? So we had SISO, SISO. There are two ways based on the direction of flow of the data from left to right, from right to left. We have PISO, we have SIPO, and we have PIPO. Now, these 5 we have seen, but these 2 we haven't. So just quickly, without going into too much details of what these registers are, basically what they do is, and you can see from the diagram itself, that it is a shift register. Data goes in from the left to the right. The only difference is it doesn't come out like it does in this case, right? It's not coming out. It's just a feedback loop. So whatever output we get, we just put it back in, right? So just what it does is it rotates the data, right? That's what it's doing. This is also the same thing. This is also SISO. There's no output though, right? So nothing is coming out. Whatever comes out is basically just fed back into the system. So if you had to rotate your data to the right, you could use this type of register. And if you had a 4-bit data that you wanted to rotate to the left, you could use this kind of register, right? So this is all we're going to talk about, these 2 kinds of registers, just for you to understand that using shift registers, you can design something that shifts your data to the right, and you can design something that shifts your data to the left. All right, so that's it for this video. So far, we have discussed the 4 main kinds of operations of shift registers: serial input, serial output, serial input, parallel input, serial output, and parallel input, parallel output shift registers.